In our previous lecture on relativistic quantum mechanics, we had met the Klein Gordon equation. We had discussed how Schrödinger had arrived at that equation, and we had also discussed the shortcomings like the existence of negative energy solutions and a non-positive definite probability density, which led Schrödinger and the other originators, including Klein and Gordon, to give up on this equation, at least for the time being. However, the particular equation that we are talking about happens to be a very important equation in physics. While it does not really give us a fully satisfactory theory of quantum mechanics involving single point particles, it actually is the starting point for the study of scalar fields in quantum field theory. As a result, it is actually very important to study this equation in some detail, which is what we are going to do in this and perhaps the next lecture. Before we go on to another equation which is slightly more successful as an equation for single particle quantum mechanics. At the beginning, let me just recapitulate whatever we had learned about the Klein Gordon equation in the previous lecture, but we will do this using a slightly different notation. Because this is a relativistic theory, we will use a notation which is more relativistic in nature, so that later on, going over to relativistic quantum field theories from this will be much easier. I am going to assume that you are all familiar with the basic notions of Minkowski metric and about contravariant vectors and their covariant counterparts. Just to fix things, let me stress that here I am going to use the metric eta mu nu, which is mostly minuses, that is, plus, minus, minus, minus. Eta mu nu, of course, is a second rank tensor which can be written down in the form of a 4x4 matrix. It's a diagonal matrix with plus 1 in the 0, 0 position and minus 1 in the other ith positions. Also, just to remind you, the covariant counterpart of a contravariant vector can be obtained by lowering using this eta mu nu. A mu is going to be equal to eta mu nu A nu. Here, of course, we are using the Einstein summation convention that repeated indices are going to be summed over unless explicitly stated otherwise. And because of the simple form of the Minkowski metric, what this does is that it keeps the zeroth component the same and changes the sign of all the non-zero components. So in particular, if you're looking at the energy momentum 4 vector P mu, P upper mu, that is the contravariant version, has P0 and P vector as its components. P lower mu, the covariant version, has components given by P0, which is a P lower 0, which is the same as P upper 0, and minus P for its spatial components. P upper 0 and P lower 0 are both equal and equal to energy by the speed of light. This extra factor of speed of light is essential in order to ensure that all the 4 components of this 4 vector have the same dimension. The invariant product P lower mu P upper mu, which of course is a norm squared of the metric of the energy momentum vector P mu, is actually easily seen to be P0 whole square minus P vector square, and this is an invariant quantity which is given by m square c square. This is standard relativistic physics. Of course, we know this equation perhaps better as E square equals P vector square c square plus m square c to the 4, which is an immediate consequence of rewriting this equation with P0 equal to E by c. Now, in order to quantize an equation like this, what we need to do is replace the energy E by IH cross del del T and P vector by H cross by I grad, which is something which we have already done before in the last lecture. But in the relativistic version, instead of using E, let's use P0, which makes this IH cross del del T over C. And remembering the CT is X0, this is IH cross del del X0. Or what is a standard useful abbreviation? IH cross del 0, where del 0 is del del X0. The lower index on del 0 is a signifier that when you differentiate with respect to the components of a covariant vector, you end up with a contravariant vector. On the other hand, minus p vector, the spatial part of p lower mu, the covariant p, is given by I h cross del del xi, where the I h cross is there because of the extra minus sign which you get when you bring the I from the denominator to the numerator. But we can couple all of these together. Remember, P0 is the temporal part and minus P vector is the spatial part of the covariant P vector, P lower mu, and P lower mu thus. And what these replacement rules just tell us is that P lower mu can be replaced by I h cross del lower mu. And similarly, P upper mu can be replaced by I h cross del upper mu. Now going back to the energy momentum relation, which is P mu minus m square c square equals 0, this can be converted into a quantum mechanical equation by making this act on phi, giving 0, and then replacing the P lower mu by I h cross del lower mu and P upper mu by I h cross del upper mu, and this gives us I h cross whole square del mu del upper mu minus m square c square acting on phi equals 0, and realizing that this del lower mu del upper mu operator is what we call box or D'Alembertian. This is really del 0 whole square minus del 1 square del minus del 2 square minus del 3 square. In other words, del 0, remember, is derivative with respect to Ct. So this is 1 by c square del 2 del t2 minus Laplacian, our familiar four-dimensional analog of the Laplacian operator, and dividing our equations through by h cross square simply gives us box plus m square c square by h cross square acting on phi is 0, which let me remind you is the Klein Gordon equation. We have just recapitulated the derivation of the Klein Gordon equation that we had done in the last class, but we have done this using a more relativistic notation than the one we used in that class. You will soon see why the relativistic notation makes things much simpler, but for today's class we are going to sort of mix between the two notations. Sometimes we will use relativistic notation, sometimes we will lapse back to the standard pre-relativistic notation. Let us quickly continue with the recapitulation part and talk about the two basic results that we had derived for the Klein Gordon equation, both of which went against the use of Klein Gordon equation as a single particle equation. So the first of these were the so-called probability density conservation. Let me just show you how the derivation goes using this relativistic notation. We start with del mu del upper mu plus m square c square by h cross square phi equals 0. We then convert that to a complex conjugate, but note that phi is the only complex quantity here. So everything else stays the same. The phi gets replaced by phi bar. Then as a standard, you are going to multiply the first equation by phi bar and the second equation by phi and subtract. And this will make the m square c square by h cross square phi bar phi term cancel out. And you are going to be left with phi bar del mu phi minus phi del mu phi bar equals 0. And this is actually the same as del mu, a total 4 divergence of phi bar del mu phi minus phi del mu phi bar. I'm pretty sure you have all recognized, I'm pretty sure that you have all seen this done before. And even if you haven't, you should recognize what we have done here. We have just simply used the same sort of calculation that we used for Green's theorem in ordinary 3D vector calculus. However, since this kind of notational jugglery may be a bit unfamiliar to some of you, let me just show you how this works out in some detail. Let me just show you what the first term here actually means. Del mu of phi bar del mu phi, of course, as a summation over the index mu, but that is something which the notation will take care of. All we have to worry about is the fact that del mu is a derivative, and like all derivatives, when it acts upon a product, it gives you two terms like this. One in which the derivative acts on the first factor, the other in which the derivative acts on the second factor. Now note that the other term that you have in the equation that we just wrote down at the bottom of your screen, del mu phi bar, when you apply del mu on that, you actually get one term, del mu phi del upper mu phi bar, which is exactly the same as this one. So when I subtract, the two will cancel. If this is completely unfamiliar to you, you may be slightly confused by the fact that here the del upper mu is on phi and here the del upper mu on this term is on phi bar. But you should realize that since the lowering and raising of these indices are being done by eta mu nu and its inverse eta upper mu nu, you can easily raise and lower the same index simultaneously. Even though your calculation involves derivatives, that's not a problem because eta mu nu is a numerical constant tensor. Okay, this is just one term. The other term is plus phi times del mu phi bar. Of course, when you subtract these two quantities, you exactly get the upper line in green here. So, this calculation does show that what we have ended up with is a 4 divergence, a divergence with respect to del 0, del 1, del 2, del 3 of the quantity phi bar del mu phi minus phi del mu phi bar. So you can write this as del mu j mu equals 0. And just to remind you, del mu j mu is nothing but del j0 del x0, that's del 0 of j0, plus del I of ji, and del I ji is nothing but the divergence of j. So this equation really translates to del rho del t plus divergence of j, our familiar continuity equation, provided we identify x0, of course, with ct, but that will necessitate us to identify j0 with 0. So this j mu 4 vector has 4 components, 0, j1, j2, j3. Once again, the 4 components of a 4 vector must all have the same dimension. This extra factor of c on the density ensures that in the resulting thing, all the components have the same dimension. From our derivation so far, j mu could be phi bar del mu phi minus phi del mu phi bar or any of its multiples. Now, phi bar del mu phi minus phi del mu phi bar is purely imaginary, being the difference of a function and its complex conjugate. So we would definitely expect to have an I multiplying this somewhere so that you get a real quantity. But apart from that, you are free to throw in any arbitrary set of constants that you want that will serve some purpose that you have in mind. In particular, what we do is define j mu by multiplying phi bar del mu phi minus phi del mu phi bar by this particular constant I h bar by twice m. The reason why we do this is that, as we had explained earlier in the previous video, this ensures that in the non-relativistic limit, this gives us the same expressions for rho and j as we would expect from Schrodinger's equation. Now, just to quickly tell you what this means in terms of the rho and the j, rho here, the probability density, so to speak, from this particular expression, works out to be j0 by c. By the way, since we are using the plus minus 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 metric, whether you write j0 with an upper index or a lower index doesn't matter. Both the contravariant and covariant forms of the j mu vector have the same 0th component. And that, from this expression, simply works out to be I h cross by twice m phi bar del 0 phi minus phi del 0 phi bar divided by an extra c. And since del 0 is del del x0, that is 1 by c del del t, that means there are 2 factors of c here, and this gives rise to the final form I h cross by twice mc square phi bar del t minus phi del phi bar del t. As we had seen in the last lecture, if you use wave functions which satisfy IH cross del phi del t equal to E phi, this expression is going to ultimately end up being E by mc square times phi bar phi, which in the non-relativistic limit where E is very close to mc square gives us back our familiar formula phi bar phi or phi mod square. Now what about J? Here you have to be slightly careful. The probability current vector J vector is actually the spatial part of the 4 vector J mu. But which 4 vector? It's actually the spatial part of the contravariant J mu, that is J mu with an upper index, the one which has been written down here. But now you have to remember that in J upper mu, what you have in the derivative is del upper mu. So in particular, since we are talking about the spatial part, mu takes the values 1, 2 and 3, which we typically write by convention as I. That is, we use a convention that mu, nu, etc. the Greek indices run over 0, 1, 2 and 3, and Latin indices, when they are used, they run over only the spatial part, that is 1, 2 and 3. What is very important is del upper I, where I could be either a 1, 2 or 3, is of course eta ij del j. You might object and say that it should be really eta I nu del nu, but eta I nu, where nu is 0, will always vanish. So basically all this eta does is that it changes the sign of del I. So del upper I is actually minus del lower I, which is actually our space derivative. So when you consider J1, J2, J3 with upper indices, which makes up our J vector components, the derivatives del 1, del 2, del 3 there are actually negatives of the spatial derivatives del x, del y, del z, which is why you end up with an extra minus sign, and that extra minus sign here can be seen in the form of I switching place from the numerator to the denominator. Now this is a very trivial point, but this kind of thing can often cause a lot of confusion, so I wanted to stress this part explicitly. And one more important point, of course, is that the equation that we have written down now in the relativistic form, del mu j mu, actually has the entire continuity equation del rho del t plus divergence of j in a much more compact form. And compact forms are often easier to manipulate and work with. This is what shows how convenient the relativistic notation can really be, especially when you intend to do a lot of calculation involving relativistic quantities.
Moving quickly on to the other topic that we had actually already studied in the last lecture, that of wave-like solutions of the Klein Gordon equation and the corresponding results about the energy values which such solutions have. Let me remind you that we start with the expression box plus m square c square h by h cross square phi equals 0. Just to remind you, box is nothing but del lower mu del upper mu. And if you try a wave-like solution phi, given by e to the minus I by h cross p lower mu x mu, where the p mu's are just constants, arbitrary constants at this stage, if you plug this into the Klein Gordon equation, notice that the derivatives del lower mu brings down a minus I by h cross p mu from the exponential, p lower mu that is, and del upper mu brings in an extra factor of minus I by h cross p upper mu. Putting the two together, you end up with minus p lower mu p upper mu by h cross square. Of course, the summation over mu is still implied, times phi from the first term box phi. The second term is simply m square c square by h cross square times phi. So you end up with this thing in the bracket, minus p lower mu p upper mu, the invariant norm of the 4 vector p, by h cross square plus m square c square by h cross square. This quantity must be equal to 0 because phi, of course, being an exponential, cannot be 0. In any case, phi being 0 would have rendered our solution rather useless. So in order that we do get a wave-like solution to the Klein Gordon equation, the quantities p0, p1, p2, p3 in the p mu x mu term has to satisfy P lower mu, P upper mu equals m square C square, which can be expanded out in the form P0 whole square, that's P0, P0, P lower 0, P upper 0, minus P vector square. The minus sign comes in simply because when you lower the index mu to get P lower mu, you get an extra minus sign from the eta mu nu. P0 whole square minus P vector square has to be equal to m square C square, which of course is our familiar energy momentum connection if you interpret P0 as E by C. Now notice that this actually tells you that P0 can have two different values because P0 whole square is what this equation gives you. The point is, for any given momentum P vector, you can actually get two solutions. One where P0 is the positive square root of P vector square plus m square C square. The other where P0 is the negative square root of P vector square plus m square C square. This means that, as we had already explained before, negative energy solutions to any quantum equation of this kind, something which at its heart obeys E square equals P square C square plus m square C to the 4, is inevitable, and you can see an example of that in action here. Now, just to summarize, we have two solutions here for any given P vector value, and these two solutions can be written down as solution number 1 and solution number 2. Notice that in both of these we have chosen P0 to be the positive square root of P square plus m square C square, but the term with P0, P0 Ct, comes with a factor minus I by h cross in the first expression and plus I by h cross in the second version. These two solutions have been labeled with superfixes 1 and 2, and 1 of course corresponds to the standard positive energy solution, 2 corresponds to a negative energy solution. In case you're confused about where the negative energy comes from, just remember that if you apply IH cross del del T on phi P1, you're going to get plus P0 times C. That's the energy for that particular solution. If you apply the same operator on phi P2, you would get a factor of minus P0C. You would get an energy eigenvalue which is negative. Both of these can be compactly written in the form phi PR of x, where R can take either value 1 or 2, given by e to the minus I by h cross times epsilon R P mu x mu. Epsilon R is a factor which is either plus 1 when R is 1 and minus 1 when R is actually 2. So both the solutions can be rolled up into this one equation. Now you may have noticed one thing. What we have done is we were bound to change the sign of the energy term in the two solutions, but we have also changed the sign of the momentum term in both of them. So the second solution actually corresponds not to a momentum eigenvalue P vector, it corresponds to a momentum eigenvalue of minus P vector. This is something which you have to bear in mind. This means that while phi P1x corresponds to an energy eigenvalue of plus P0C, square root of P square C square plus M0 square C to the 4, and a momentum eigenvalue of plus P, the second solution phi P2x corresponds to an energy eigenvalue which is minus P0C and a momentum eigenvalue of minus P vector. This minus sign is a very important thing to bear in mind. You might of course have equally well written a solution with phi P2x taking the form e to the I plus I by h cross P0 Ct plus P dot x instead of minus P dot x as we did here, and that would have actually given you a momentum eigenvalue of plus P. But remember, you get a solution for all values of plus P, so choosing minus P is not a problem. But there is a deeper reason why we are doing this. We will see later that these two solutions actually correspond to two different kinds of particles. As I said earlier, the Klein Gordon equation does not make sense as a single particle equation. But it does make sense as an equation which describes the quantum field, and in the field theoretical version, phi p1x and phi p2x essentially corresponds to a particle and its antiparticle. The negative momentum minus p actually is very important in that interpretation. We are going to come to that later, but for the time being, let me just put you on notice that our notations of phi p1 and phi p2 is chosen in such a way that they are energy eigenfunctions and momentum eigenfunctions. It's just that not only is the energy eigenvalue opposite of each other, so is the momentum eigenvalue. That in itself is not a problem, but what is the problem is that you have to remember that we are using the label P to specify which particular phi we are talking about in both the cases. Where the label P is the momentum eigenvalue for the solution of the first type, it is not the momentum eigenvalue for the solution of the second type. For the solution of the second type, the momentum eigenvalue is actually minus P. At the end, this is nothing but a notational issue, but this notational issue will become very convenient when we talk about antiparticles later. Talking of antiparticles, as we all know, particles and antiparticles differ from each other in being opposite in some respects. And one of the most important of these respects is electrical charge. If a particle is charged, then it and its antiparticle responds to electromagnetic fields in exactly opposite fashion. So this is a good point of time where we can start talking about the way in which charged scalar fields or charged particles which obey the Klein Gordon equation interact with external electromagnetic fields. Now, for this, we will need a bit of background which you must have picked up in your classical physics course. In classical physics, of course, a free particle is defined by a Hamiltonian given by p square by twice m. I'm talking about non-relativistic classical physics, of course. Now, the way in which you incorporate electromagnetic interactions of this particle with charge q with an external electromagnetic field is as follows. This procedure is called minimal coupling, and if you adopt it, you will find that the resulting equations of motion exactly describe the Lorenz Force Law acting on a particle with charge in an electromagnetic field. And the procedure is to replace the Hamiltonian h by h minus qv. The energy shifts by qv, and the momentum p shifts by q times a vector, where a vector is a vector potential. Of course, v that we mentioned earlier is a scalar potential. So the new Hamiltonian for a charged particle becomes p minus qa whole square by twice m, and the minus qv can be shifted to the other side to say h is p minus qa whole square by twice m plus qv. So this is the form of the Hamiltonian for a charged particle in an electromagnetic field. And if you have not seen this before, I urge you to write down the canonical equations of motion from this, and from that show that you actually do get the Lorenz Force Law. That is, a force acting on the particle which is given by q times E plus V cross B, where E and B are related to the scalar and vector potentials by the standard relationship that we learn about in electrodynamics. Now this minimal coupling carries over perfectly well to relativistic mechanics as well, and there the formulation looks rather elegant if you express this in relativistic notation. The basic idea is that now we are going to ask, how would you change the energy momentum 4 vector in the presence of an electromagnetic field? So the zero component of this energy momentum 4 vector is E by C, and by the rule that we laid down before, E by C gets shifted to E by C minus QV by C. There's an extra 1 by C factor here, of course. And P vector, as before, shifts to P minus Q times A vector. Now these two can together be combined into a 4 vector relationship, which is rather elegant. P mu gets shifted to P mu minus Q times A mu, where A mu, this 4 vector, is called the potential 4 vector,
and its zeroth component is the scalar potential V divided by C, and the spatial components is nothing but the vector potential. Now here, let me point out one issue which might confuse people sometimes, especially if you refer to different books. The presence or absence of this 1 by C factor in the 4 potential may very well depend on which book, or more precisely, which system of units you are using. In the SI system of units, let me remind you that the Lorenz force equation is actually written F equal to QE plus V cross B. And that goes to show that the electric and magnetic fields in this particular system in SI do not have the same dimensions. The electric field has a dimension which is the dimension of speed, maybe the speed of light or whatever, some speed, times the dimension of the magnetic field. On the other hand, to contrast with this, in the CGS or old MKS system, people often use this particular form for the Lorenz Force Law. And in this version, E and B have exactly the same dimension. So that of course translates also to the scalar and the vector potential. In this particular second unit system, V and A would have the same dimension, but in SI, V's dimension is speed times the dimension of A, and that is precisely why the potential 4 vector must have a 1 by C in the zeroth component to ensure that all the components have the same dimension. And this also goes with the fact that in the CGS system, this minimal coupling for 4 vectors would have been written down in the form P mu gets replaced by P mu minus Q A mu by C. Once again, a factor of 1 by C is needed for dimensional consistency there. In SI, there is no 1 by C. In the minimal coupling formula, there is a 1 by C in the 4 vector for the potential. These equations may look slightly different depending on your choice of units, and this is why I am warning you at this stage. Especially if you refer to some book, you may see a formula which looks slightly different. That would usually be because of a different choice of units. In this lecture, we are going to use SI units. So for us, P mu is going to be P mu minus Q A mu. Let us now ask the question, if we were to carry out the same prescription on a Klein Gordon equation, that is, we replace P mu by P mu minus Q A mu in this equation, what does that tell us about the interaction of a charged Klein Gordon particle with an external electromagnetic field? And the answer is pretty straightforward. All you have to do is start with the Klein Gordon equation, which we have written using P mu explicitly, but you must remember P mu has to be replaced by IH cross del mu in order to get the quantum mechanical version of this equation. And then this simply becomes P mu minus Q A mu with lower indices mu times P upper mu minus Q A upper mu. This operator minus m square c square acting on phi equals 0. Remember, P mu actually here is a differential operator IH cross del mu. So if you were to replace the components, this simply would translate to this version of the equation. 1 by c square times IH cross del t minus QV whole square. That is the P0 minus QA0 whole square minus the dot product of P vector minus QA vector with itself, and that gives you this term H cross by I grad minus QA whole square minus m square c square as before, acting on phi equals 0. So this is the equation which a charged Klein Gordon particle in an external electromagnetic field will obey. Now, since the Klein Gordon equation has been modified in the presence of an electromagnetic field, it stands to reason that various properties of this equation that we had derived earlier would also get modified in the presence of an electromagnetic field. Let me just illustrate what this does to the equation of continuity. For example, So we start with the Klein Gordon equation, which now reads IH cross del mu minus QA mu times its contravariant component part acting on phi minus m square c square phi equals 0. And let's expand this out in full. Now the expansion is pretty straightforward. The first term actually gives rise to 4 terms when you open it up. Minus h cross square del lower mu del upper mu phi, which remember is actually minus h cross square box phi. But we leave it here in this particular form. That's one term. Then you have a term in which IH cross del mu is taken from the first bracket, QA mu is taken from the second bracket, acting on phi. That's actually going to give me the third term written in blue in that equation, because del mu is now acting on a mu phi. On the other hand, if you take minus QA mu from the first bracket, IH cross del upper mu from the second bracket and make that act on phi, you get the second term in blue, and you also get plus q square a lower mu a upper mu times phi. That's the final term from the first piece in the Klein Gordon equation. Of course, you bring this up at the end with minus m square c square times phi. This is equal to 0. Now, as in the case of the derivation that we did when we did not have any electromagnetic field, all you have to do is take the complex conjugate of this equation, which is the equation which we have written down in black. Of course, complex conjugation essentially changes the phi's to phi bars and the i's to the negatives. So that's what the equation really becomes. The second and the third terms, which have an explicit I, change sign, and all the phi's get replaced by phi bars. The next step is pretty standard. All we do is multiply the first equation, the one in blue, by phi bar, the one in black by phi, and subtract the two. And if you do that, what you are going to get is this. 0 must be equal to the first term, which is exactly the same as the term that we had without electromagnetic fields, minus h bar square times phi bar box phi minus phi box phi bar. In addition, you have an extra piece, which is minus I h bar q taken common. Then you have two terms which come from the original equation, the one involving phi after multiplication by phi bar, and the terms in black come from the second equation, the one which was originally written in black after multiplication by phi. Now, we already know that the term in red in the bracket is actually a total 4 derivative, del lower mu acting on phi bar del upper mu phi minus phi del upper mu phi bar. We had already seen this before. What is actually pretty gratifying is that despite this additional complication which the electromagnetic field has brought upon us, we still can get this expression to be a 4 divergence, because if you look at the terms which are in the other bracket, then the first term, a mu phi bar del mu phi, and the last term, phi times del mu of a mu phi bar, actually together give you a total derivative of del mu, 4 derivative, del mu of a mu phi bar phi. The second and the third terms actually give you the same 4 derivative del mu of a mu phi bar phi. And if you put them together, this expression simply becomes minus h cross square times del lower mu acting on phi bar del mu phi minus phi del mu phi bar, which is exactly what we had earlier without electromagnetic fields. The presence of the electromagnetic field has added one extra term. You have got twice IQ by h bar, a mu times phi bar phi as an additional piece. And that's it. So, what we have is that once again we have a 4 vector whose 4 divergence del mu j mu is 0. And j mu is going to be some multiple of phi bar del mu phi minus phi del mu phi bar plus twice IQ by h bar a mu phi bar phi. So this is exactly the same expression that we had without the electromagnetic field with an additional correction term to the 4 vector j mu. Indeed, the prefactor that we choose for J mu in this case is the same as the one we had chosen earlier. That is, we multiply our expression phi bar del mu phi minus phi del mu phi bar plus twice iq by h bar a mu phi bar phi by this factor I h cross by twice m. And from this we can easily derive, by following the same procedures as before, the probability density rho and the probability current density vector j. These turn out to be almost exactly the same as the one we had earlier, except that rho now has an additional term minus qv by mc square phi bar phi, and j is supplemented by an additional term minus q a vector by n phi bar phi. So these are the additional corrections we have to the components of J mu in the presence of an electromagnetic field. We will take a look at what these terms mean later when we talk in more detail about the interaction between charged particles and electromagnetic fields. But for the time being, let me turn to another aspect of this particular kind of interaction that we are talking about. This happens to be at the very heart of what we call modern particle physics.
What we will see now is that the minimal coupling prescription that we use to introduce the electromagnetic field's effects on a particle obeying the Klein Gordon equation is an example of what is called a gauge interaction. To understand this, let us go back to the free Klein Gordon equation P lower mu P upper mu minus m square c square phi equals 0, and consider that this particular equation is actually symmetric under a very, very familiar symmetry. As you all know, in quantum mechanics, changing the phase of a wave function by an overall factor does not change the physics. And in here also, if you change phi of x to a new function phi prime x, which differs from the original function phi of x by a multiplicative phase factor into the I lambda, where lambda is independent of x and t, so the same phase factor everywhere. This is called a global phase change. If we do that, it's easy to check that both the terms which appear in the Klein Gordon equation respond very, very simply. The term m square c square phi picks up an overall factor of e to the I lambda. The term p lower mu p upper mu phi, which essentially is the box apart from a factor of h cross square, also picks up the same factor e to the I lambda, simply because the factor e to the I lambda, being a constant, is not acted upon by the derivatives which are there in the terms p mu. Remember that although we are calling these terms p mu, they are really IH cross del mu's, but they don't act on e to the I lambda, or rather, e to the I lambda can just travel through the box and come out of it. As a result, if you look at the left-hand side of the Klein Gordon equation, the factor p mu minus m square c square phi just picks up an overall phase factor e to the I lambda and becomes e to the I lambda times p mu minus m square c square phi. And since Klein Gordon equation said that the original factor was equal to 0, multiplication by e to the I lambda still keeps it equal to 0. What that means is phi prime is going to satisfy the same Klein Gordon equation as the original phi did. So this replacement of phi by a phi prime, multiplication by a global phase factor, a phase factor which is independent of space and time, is a symmetry of the Klein Gordon equation. But it is equally easy to see that a local phase change is a different story. If you change phi of x to phi prime of x by multiplying phi of x by a phase factor which depends on space-time coordinates, so now my lambda is no longer a constant, it's a function of x, then the term m square c square phi still picks up the same phase factor to the I lambda of x. It's lambda of x now because it depends on space and time, but it just comes out of the expression.
But the derivative that is there in p mu phi complicates things the moment you have a local phase factor. So p mu phi, which is actually IH cross del mu phi, upon this substitution changes to IH cross del mu acting on e to the I lambda x phi, and by the standard magic of differentiation, this now gives me two terms. And if you couple them together, you get e to the I lambda of x as an overall factor, but that does not multiply IH cross del mu phi alone. There's another term which you get because the I lambda gets differentiated to give you I del mu lambda. So that gives you the extra term minus H cross del mu lambda into phi in the bracket there. So this is not the same as e to the I lambda x multiplying p mu phi. So you no longer have this overall phase factor coming out. This of course is with a single p mu. In the Klein Gordon equation, you have p lower mu, p upper mu, and both factors will of course complicate things a bit more, but what matters is that it's easy to see that you will not get the simple e to the I lambda x factor out, and as a result, the Klein Gordon equation will not be satisfied by the function phi prime x given by e to the I lambda of x phi x. So, the original Klein Gordon equation, the one without electromagnetic interactions, does have global phase symmetry, but not local phase symmetry. The question is, can we modify the equation in such a way that it does have global as well as local phase symmetry? The answer turns out to be yes. And let us now explore how that can be done. We don't really have to search for what has to be done, because we have already done it. We have actually replaced p mu by p mu minus q a mu in our bid to use minimal coupling. Now the question is, if we change p mu to p mu minus q a mu, do we expect local gauge transformations or local phase transformations to actually give you a symmetry? That is, do we expect that when you replace phi by e to the I lambda x times phi, will the factor p mu minus q a mu acting on phi change by picking up just an extra phase factor of e to the I lambda x? Well, the answer to that is yes, but what you have to do is something slightly more than just replace phi by e to the I lambda x times phi, because note that when you carry out this transformation, p mu minus q a mu phi becomes p mu minus q a prime mu phi prime. What we are assuming is that when we are carrying out this transformation on phi by multiplying it by a local phase factor, at the same time we are also transforming our vector potential A in some particular manner. This is of course the 4 vector a mu that we are talking about, and that is being replaced by a new 4 vector a prime mu. Now what we already know is that p mu phi prime will become p mu minus h cross del mu lambda phi times e to the I lambda x. That's something we had just worked out. So basically, what we are going to get here is that upon this pair of substitutions, phi going to phi prime and a mu changing over to a mu prime, what you will have is an overall phase factor to the I lambda x multiplying p mu minus h cross del mu lambda minus q a mu prime acting on phi. What we want is that this should be e to the I lambda x times the original term, that is e to the I lambda x times p mu minus q a mu acting on phi, and for that all we have to demand is that this extra piece that you have, h cross del mu lambda, gets absorbed in the transformation which connects a mu and a mu prime. That is, we are demanding that h cross del mu lambda plus q a mu prime is q a mu. So this tells me that in addition to actually changing phi by multiplying by a local phase factor, what we need to also do is change a mu to a mu prime in this particular manner. you have to essentially get mu prime is mu minus h cross by q del mu lambda. So what we have achieved is that if we make a transformation which multiplies phi by a local phase factor and at the same time changes mu by this additional piece minus h cross by q del mu lambda, then p mu minus q a mu phi just picks up an overall phase vector to the I lambda x. Now what happens to the thing which is actually sitting in the Klein Gordon equation? Of course, there, this factor p mu minus q a mu phi is acted upon further by another operator p upper mu minus q a upper mu. And that essentially now becomes p upper mu minus q a upper mu acting on e to the I lambda x times p lower mu minus q a lower mu phi, but that is just e to the I lambda x times some function of x. And just by following the same calculation as before, this is going to essentially just pick out an overall factor of e to the I lambda x. As a result, both terms which are there in the Klein Gordon equation, this one which involves derivatives and hence by itself would not have picked up just a phase factor under a local phase transformation, but now with this mu introduced and changing in this particular manner does, and the other term minus m square c square phi, both these terms pick up a factor of e to the I lambda, and that means that the new phi along with the new mu of course does satisfy the Klein Gordon equation once again. So the equation of motion stays unchanged under this transformation. Phi x goes to phi prime x equals e to the I lambda of x phi x. But for that we have to do two things. We have to replace p mu in the Klein Gordon equation, in the original Klein Gordon equation, by p mu minus q a mu, which of course is what we did and called it minimal coupling, and demand at the same time that a mu transforms simultaneously by this law that a mu goes over to a prime mu, which is a mu minus h cross by q del mu lambda, or essentially the same thing as saying a mu changes by a fourth derivative, a del mu chi. And this chi is nothing but our lambda, the phase factor, times h cross by q. So what we do is change the wave function by a phase and change the four vector potential by a fourth derivative essentially of that phase with an additional factor. And when we do that, this keeps the Klein Gordon equation unchanged, but note that this transformation that we are doing on the vector potential is already familiar to us from electrodynamics. This is exactly what we mean when we say we are going to carry out a gauge transformation. Now, in case you have actually studied the gauge transformation in electrodynamics in non-relativistic notation only, in which case you know that the vector potential H changes by picking up a gradient of a scalar and V changes by picking up a derivative of that same scalar with respect to time, I will urge you to check for yourself that when you express that in the language of the four vector potential, this is exactly the same as that gauge transformation that you have already learned. So, to summarize, what we can say is the introduction of the electromagnetic field into the Klein Gordon equation via minimal coupling, along with the familiar gauge transformation that leaves electric and magnetic fields unchanged, is actually something that's going to keep the Klein Gordon equation intact when you carry out a local phase transformation. A global phase transformation is a symmetry of the Klein Gordon equation even without the vector potential or without changing the vector potential in any way if it's there. But in order to ensure that the equation is also symmetric under the local phase transformation, you need to first of all introduce the vector potential in the equation by doing minimal coupling,
and insist that the vector potential undergoes a gauge transformation along with the phase transformation of your wave function phi. To summarize, the quantum theory of charge-matter interaction, as we already know it, has local phase symmetry, which is also called local gauge symmetry. That is, we already knew that in order to incorporate electromagnetic interactions, we have to replace P mu by P mu minus Q A mu. We already knew from electrodynamics that A mu has a symmetry. That is, the physics does not change when you replace A mu by A mu minus del mu chi. And putting all this together, we can check that the equation becomes local gauge symmetric. You can change the wave function phi by an arbitrary phase factor which changes from point to point, and yet the equation will still stay valid. What makes this extremely important is that we can actually turn this around on its head. Instead of saying that electromagnetic interactions already has this particular feature, we could have started with assuming that we know nothing about electromagnetic interactions, but we want our theory to be symmetric under a local phase change. This is technically called a local U1 symmetry because all these phases taken together form a group called the U1 group, the group of unitary 1x1 matrices. Now, under this particular abelian group, our original equation that we had written down earlier already had global symmetry. That is, if you were to change the phase of phi everywhere by the same factor which you take from U1, then the equation would be symmetric. But if we go further and demand that this symmetry be a local one, technically we call this gauging the symmetry. If we do that, then we have to demand the existence of a gauge field A mu. We have to incorporate minimal coupling in our theory, that is P mu has to be replaced by P mu minus Q A mu, and we have to demand that A mu will transform in a particular manner. Now, why is this so important? As far as electromagnetism is concerned, this is just another way of looking at what we already know, so nothing new is going to be added to our information base by demanding this. However, at the time when this particular gauge symmetry was discovered, there used to be many other interactions for which we did not have a full-fledged theory. If we demand that even in such cases, an already present symmetry which is global in nature can be gauged, can be replaced by a local symmetry by changing derivative terms, modifying them by adding additional gauge fields and demanding that the gauge fields transform in a particular manner when you carry out this local gauge symmetry. It turns out that gauging a global symmetry is the path to other interactions. In fact, is a path to almost every known interaction that we have. And this leads eventually to what we call today the standard model of particle physics. The interaction is formed by this particular gauge group, SU3 cross SU2 cross U1. Global elements from that group acts as symmetry elements in the theory free of interactions, but demanding that the local versions which change from point to point in space and time, also has to be a symmetry, needs you to modify the equations in a very particular way, and this leads to our basic theory about strong and electromagnetic and weak interactions. What I want to point out is that the seeds of gauge symmetry is laid down in the way in which a Klein Gordon particle would interact. By the way, I should not really stress the Klein Gordon nature of the particle too much here, because all electromagnetic interactions essentially involve the same basic structure. You have to replace P mu by P mu minus Q A mu, that is, introduce a gauge field and demand that A mu changes by picking up an extra minus del mu chi type of term. Now, the full theory of gauge interactions is, of course, rather complicated and definitely beyond the scope of this course, but you will learn more about it later on in particle physics.
In the next lecture, we will turn to some other aspects of the Klein Gordon equation. For example, how we can treat the Klein Gordon equation as a consistent theory for single particles, at least when there is no interaction between the particles. We will introduce an inner product which will convert the collection of all positive energy solutions of the Klein Gordon equation into an inner product space, more specifically a Hilbert space. We will also see the turning on interactions will cause problems with the structure, which is why we will have to abandon this until we return to it as a quantum field theory. However, the scalar product that we will introduce will turn out to be very useful, not only in the theory of single spin zero particles, which the Klein Gordon equation tries to describe, but also for use in the corresponding quantum field theory. But all this is for the next lecture. Let me sign off for now.